So in this lecture we will continue to study the characteristic functions of random variables. So I'll start with the Lévy continuity theorem, which states as follows. So you consider xn a sequence of random variables, and you represent by fxn the characteristic functions of the random variable xn. So I will assume first that fxn t converge to phi of t for all t in R. So this is the first assumption. And then a second assumption is that phi is continuous at t equal to 0. Then what I claim is that xn converge in distribution, which means that, well, if you consider mu n, the distribution measures of these random variables, then there exists mu such that, which is a probability measure on R, such that mu n converge to mu weakly. And so you can compare this theorem with the statement of the last theorem of the previous lecture, and you will see there that we were asking the characteristic functions to converge only in an interval which contains the origin. So here I impose a stronger assumption that actually the characteristic functions converge to all t, for all t, and that phi is continuous at 0, and then before from the assumptions we got that the sequence of distribution measures was tight. Now, well, we prove that actually it converged. So by imposing slightly stronger assumption, or a stronger assumption in the sense that now we are requiring the characteristic functions to converge to all t, we get not only the tightness but the convergence. And the proof, it's a nice example of how you prove that a sequence of probability measures converge weakly to another measure. Goes in two steps. You first prove that the sequence is tight, and then you prove that the limit is unique. So there are two steps. The first step is compactness, which means tightness in this context. So we have to prove that the sequence is tight, but that has already been proved. So that follows from the previous theorem, because in the previous theorem, well, the assumptions of the previous theorem are satisfied, which means that, remember, the previous theorem were requiring the characteristic functions to converge in an interval which contains the origin to some function which is continuous at 0. So tightness is guaranteed by the previous theorem, and now we have to prove uniqueness. So to prove uniqueness, I will consider two subsequences, nj, so that's a subsequence nj which I will assume converge to some measure, probability measure nu1, and then another subsequence n prime k, which is converging to n nu2. So I'm assuming, well, that there are two different subsequences which are converging to one to nu1 and the other to nu2, and what I want to guarantee is that nu1 is equal to nu2. And this convergence is of course a weak convergence. So in particular it follows that, remember that the characteristic functions of a random variable x, it's given by the expectation of itx. So this is a bounded continuous function, and therefore it follows from the weak convergence that the characteristic functions of the random variable x and j converge to the characteristic function associated to the measure nu1, and this for all t. And also, by the same reason, the characteristic function of the sequence nk prime t, it's converging to the characteristic function associated to the measure nu2, and this for all t in R. But by the second assumption, by the first assumption, I'm sorry, the sequence is converging to phi of t, so since this subsequence is converging to phi nu1 of t is equal to phi t by the first assumption, and the same thing here. Phi nu2 of t is equal to phi of t, and this for all t in R. And this means, therefore, that phi nu1 of t is equal to phi nu2 of t for all t. So we just proved that the expectation of I tx nu1 dx it's equal to the expectation or the integral of I tx nu2 dx for all t. And we have seen in a previous theorem that since this holds for all t in R, we have that nu1 it's equal to nu2, because we can deduce from this identity that the expectation of a continuous bounded function it's equal, and therefore that the two measures are equal. And therefore we just proved that indeed if we have a subsequence which converges to nu1, another subsequence which converges to nu2, then nu1 it's equal to nu2, which proves uniqueness of the limiting point. And we have seen before that tightness and uniqueness of the limit points guarantee the convergence of the whole sequence. So we proved that the sequence of probability measure mu and converge to a probability measure nu, and in particular that the characteristic, that phi t is the characteristic functions of associated to mu. So not only, well, if this holds, then phi is necessarily a characteristic function. So that completes the proof of the theorem. Now let me prove a proposition which is very useful. So I consider a random variable x, and I assume that it has finite kth moment, so that the absolute value of x to the power k it's finite for some k larger than 1. And now what I claim is that if this is the case, we have an expansion of the characteristic function at 0, so that phi x at t can be written as the sum from j from 0 to k of I t to the power j, j factorial, exponential, the expectation of x to the power j, plus tk divided by k factorial divided by a remainder which I'm calling rk of t. And rk of t has two properties. First, that it is bounded by 4. So rkt is bounded by 4 for all t in R. And second, that the limit as t goes to 0 of rkt it's equal to 0. So, well, maybe here let me remove the absolute value, this is equal to 0, and here I forgot a term, so this is bounded by 4 times the expectation of x to the power k. So this is what I claim. So if the random variable has a finite kth moment, then you can write an expansion up to the order k of the characteristic function around t equal to 0. So this is what I want to prove now. So the proof is quite long. For this reason, I erased the blackboard, and I will start from a Taylor expansion of a function with integral remaining. So let me assume that f it's a function which is k times continuously differentiable, and what I claim is that we can write f of y, so I'm doing an expansion around 0, so that will be equal to the sum from 0 up to k minus 1 f, the jth derivative of f at 0, so that represents the jth derivative of f at point 0. This is divided by j factorial y to the power j, and plus a remainder, and the remainder can be written as follows. So this is the integral from 0 to y of f k at z x minus z to the power k minus 1 divided by k minus 1 factorial dz. So this is just the Taylor formula in which the remainder is written in the integral form. So I will start from this equation and I will slightly modify this remainder in order to get the formula I want. So let me write this remainder as f k z minus f k of 0 times x minus z k minus 1 factorial dz. And then I have here, subtracted, so let me add this term. So this term is f k at 0. There is a k minus 1 factorial here. And now you see that I'm integrating x minus z from 0 to y, or I'm sorry, here I wrote x, so let me correct that, that's y. X hasn't been introduced, so that's y. Sorry for that. So y minus z, so I'm integrating y minus z from 0 to y, is the same thing as integrating z to the power k minus 1 from 0 to y, and that gives me y k2 divided by k. So instead of writing the remainder in this form, I will add this term, which is the k term in this sum, and instead of having that remainder, what I will have is this remainder. So I will just erase and start again from this new formula in which I changed this remainder. So this is the formula we obtained up to now. So here I changed k minus 1 to k, and here I introduced this term. Now what I want to apply this formula to f of y equal to cosinus y and f of y equal to sinus of y, and then multiply what I have by I. Once I do that and I sum the two expansions, what I get is that I, and I'll take y at the end to be t times x. So again, I will apply this formula for cosinus, then for sinus. The one for sinus I multiply it by I, and then I replace y by tx. And this tells me that I tx, it's equal to, so if you do the computation here, what will appear, it's exactly j from 0 to k of I tx to the power j factorial. So I'm including yj here with the I power I, and then the remainder. And the remainder, I will write it as a k tx. And what is a k tx? Well, it's equal to a1 k tx. So this corresponds to the cosinus part plus I times a2 k tx. And this piece corresponds to the sinus part. So let me write what is a1 k tx. And you can guess what is a2 from this formula. So a1 k, it's just this integral in which I replace f by cosinus and y by tx. So this is the integral from 0 to tx, cosinus, the kth derivative of the function cosinus at z, minus cosinus k at 0, and then this is multiplying y, it's now tx, minus z, to the power k minus 1, k minus 1 factorial, dz. I'm sorry, this is a long computation. I'm giving all details, so well, you can speed up the video if you wish. And now what I'm doing, the last step will be to change variables here. So let me call z, that will be t z hat. So I'll do this change of variable in this formula. So when z is equal to tx, I get that z hat is equal to x. So that becomes an integral from 0 to x. Here I have cosinus k z, now it's t z hat, minus cosinus k 0. Tx z, it's t z hat, so I get a t to the power k minus 1, which I will write it here. And there I get z hat minus z to the power k minus 1. I'm sorry, tx. Here I have tx minus z. Z is t z hat, so the t gets out, and what I get is x minus z hat, k minus 1 factorial, and dz, it's t times dz hat, so I get dz hat, and here an extra t, so it's t to the power k. So now let me push the k minus 1 factorial outside, and let me write it as k factorial. And so here I divided by an extra k, so let me place this extra k here. And so this will be the definition of tk divided by k factorial, what I'm calling a1 k t and x. So a1 is this integral, what's appearing here. And I have tk k factorial. So up to now, what I did is I wrote exponential itx as this sum plus a remainder. The remainder has two parts, a1, a2. a1 can be written as tk k factorial times a1, and I do the same thing for a2. So now I will erase everything. I will just keep this formula and the equations for a1 and a2. So this is the formula which we obtained, exponential itx. It's equal to the sum, I separated x from t, plus tk k factorial times a1 plus I a2. a1 it's given here, a2 it's the same thing, in which I replace cosinus by sinus. Now at this point I will replace x by the random variable x, and I will take the expectation on both sides of this identity. So when I take I replace and then I take the expectation, what I get is the characteristic function computed at t. Then the first term on the right hand side, well, is just by linearity is just the sum from 0 to k of I t to the power j, j factorial, then the expectation of x to the power g. So this is exactly what we wanted. And now we have plus tk, k factorial, and r, what I will call r1 kt, where r1 and plus I r2 kt, and where r1 kt, it's the expectation of a 1 k t x. So you replace in this equation x by the random variable x, and you take its expectation, and this is the definition, and this identity follows from this identity. So now what remains to be proved, it's a bound for rk1, the same one will apply to rk2, and then to study the limit of rk1 t as t goes to 0. So this is the formula we obtained for the characteristic function. It's equal to this sum plus this remainder, where r1k is given by this expectation, in which I have here the random variable x, and here x also, and r2 it's the same thing, in which cosinus it's replaced by sinus. So now, well, let's complete the proof. I need first a bound on r1 kt. Well, but let me take, so this is the absolute value of the expectation. This is bounded by the expectation of the absolute value. This is bounded again by taking here the absolute value of x and here the absolute value. Well, this difference, the derivative of the cosinus, it's always bounded by 1 in absolute value. So this is bounded, the absolute value of this expression is bounded by 2. So this means that this integral, I have k, I have here an integral from 0 to x minus z to the power k. This gives me x to the power k divided by k. So this is equal to xk. So here there is the expectation. So this proves that this expression is bounded by 2 times the expectation of x to the power k. And this bound is uniform in t. It also holds for r2. So this means that the absolute value of this expression is bounded by 4 times the expectation of the kth power of the absolute value of x, as we claimed in the statement of the proposition. So this is the first bound. So now let's go to the second bound. This is again bounded by 2, which means that this expression, the absolute value of this expression, so the absolute value of this expression, it's bounded by 2 times this integral, and we have seen that this is bounded by the absolute value of x to the power k. So this expression, it's bounded by 2 times the absolute value of x to the power k. And by assumption, this is a random variable which has finite expectation. So the integral of this expression, it's finite. Now, let me call what's appearing here inside f tx. Right, so this is a function of the random variable x and of t. And what we proved is that this random variable, it's bounded uniformly in t by 2 times x to the power k. So ftx, it's this expression here, right? Now, if I fix x and I send t to infinity, t to 0, so if I send t to 0. So now what I'm doing is I'm fixing omega. I'm looking at what I'm claiming is that the limit as t goes to 0 of ft(x) of omega, it's equal to 0 for almost every omega. So fix an omega, this fix a value x of omega, which is finite almost surely because x has finite kth moment. So this is fix a value of x of omega. So this is ft(x) of omega. Now send t to 0. When you send t to 0, since z belongs to the interval 0x, as I send t to 0, this converges to the cosinus kth at 0, which means that this expression is converging to 0, which means that this integral is converging to 0, proving that indeed ft(x) of omega is converging to 0. So this means that the family ft of random variable, it's converging to 0 almost surely. On the other hand, this family of random variables ft(x), it's bounded by x to the power k, 2 times x to the power k, which is a random variable which has finite expectation, finite integral. So I can apply the dominated convergence theorem. So the dominated convergence theorem tells me that the expectation of the absolute value of ft(x), that this is converging to 0 as t goes to 0. And this was my second claim. So the dominated convergence theorem tells us that indeed the remainder, for as t converges to 0, the remainder converges to 0. And this completes the proof, since we already showed that Rk, the remainder, it's bounded uniformly by 2 times the expectation of x of k, as I claimed. Now I want to formulate 2 observations. The first observation is the following, that if x and y are independent random variable defined on the same space, then the characteristic function of x plus y at t, it's equal to fxt fyt. So that's very nice. That tells us that, well, if we have 2 independent random variables, then the characteristic function of the sum, it's equal to the product of the characteristic functions. And well, the proof of this identity, it's very simple. We have here that expectation of exponential I x plus y times t, so that this is equal to the expectation of itx, expectation exponential ity. Now exponential itx is the cosinus of tx plus I sinus tx, and this is multiplying the same thing with for I, replacing x by y. Now I multiply and distribute this product, so I have 4 different terms. Let me just write one of them, which is cosinus tx times cosinus ty plus 3 terms. X and y are independent. We have seen that if x and y are independent, and I take a function of x and a function of y, they are independent. Cosinus is bounded by 1, so they are integrable. So this means that the product is integrable, and the product, the expectation of the product, it's equal to the product of the expectations. plus 3 terms. And now you can again use the distribution of the product to conclude that this is equal to phi x t times phi y t, which is what we claimed. So this is a very important property of the characteristic functions. Well, to complete this lecture, I want to present an application of characteristic functions, and for that I will need this fact. So this is again an observation. Assume that x is a standard Gaussian random variable. And what I claim is that then phi x of t, it's equal to expectation minus t squared divided by 2. So I leave it to you to check that this identity holds. Now let me take two numbers, sigma, which is positive, and mu, which is a real number, and let me call y sigma x plus mu. So here, as I said, sigma, it's a non-negative non-negative number, real number, and mu, it's a real number. And let me define y by sigma x plus mu. So that tells me that y, the distribution of y, is the distribution of a normal random variable with mean mu and variance sigma square. And we also know that phi y of t, which is phi mu plus sigma x of t. We have seen a formula for in the exercise for this object, so this is exponential I t mu, then phi x sigma t, and phi x of sigma t, I know that this is equal to exponential I t mu exponential minus t square sigma square divided by 2. So that gives me the formula for the characteristic function of mean mu variance sigma square Gaussian random variable. So only these these facts in order to state the application of characteristic functions. So here is the application. Let me consider a family, a sequence xn of IID random variables. I will assume that they have a finite second moment. So let me call mu the first moment. And let me call, let me assume that exponential x1 square, it's finite. We have seen the weak law of large numbers, which means that if I take the average, x1 plus xn, and I divide that by n, this object converge in probability, and actually in L2, to mu. So if I define yj to be xj minus mu, this family yj, it's also a sequence of IID random variables, and they have expectation equal to 0. The expectation of y1 square is actually the variance of x1, and let me call that sigma square, which is finite. And what I know for these random variables y1, yn is that, well, if I subtract mu on both sides, I can rewrite this average as the average of y by n, and this is telling me that in probability and in L2 this is converging to 0. So this is what we proved by using Chebyshev inequality. Now So you see, this is converging to 0. What we will do here is that I want to multiply this expression by square root of n and to obtain that this is now not converging not to 0 anymore, and not in probability, but this is converging in distribution to a Gaussian which has mean 0 and variance sigma square. So my claim, and this is what I want to prove now, is that if you take a sequence y1, y2 of IID random variables which has mean 0 and finite variance, then square root of n times the average is converging in distribution to a normal random variable which has mean 0 and variance sigma square. So this is the same thing as saying that if I divide it now by square root of n and not n anymore, then I have a convergence in distribution to a non-trivial random variable. So this is my claim. Well, in order to prove this statement, we will use Lévy continuity theorem. So what we will prove is that the characteristic function of the random variable y1 plus yn divided by the square root of n t, that this is converging for all t to the characteristic function of a normal random variable which has mean 0 and variance sigma square. So Lévy continuity theorem tells us that, well, in order to prove this convergence in distribution, it's enough to prove the convergence of the characteristic functions, the pointwise convergence. So let's prove that. Let's consider this characteristic function, and the first thing we know is that this characteristic function is the characteristic function of y1 plus yn computed at t divided by square root of n. Now, since the random variables y1, y2, yn are independent, this is equal to the product from j from 1 up to n of yf phi yj at t square root of n. And now, since they are identically distributed, they all coincide, so this is actually phi of y1 t square root of n to the power n. And this is what I want to prove that converge. So now remember that phi of n0 sigma square t, it's equal to exponential minus sigma 2 t2 divided by 2. In order to prove that this converges to that, let me take the logarithm on both sides and prove that it converges. So when I take the logarithm, remember that this is a complex number, so I'm taking the log of a complex number. So what I need to show is that n times the log of phi y1 t square root of n, that this is converging to the log of this expression, which is minus sigma square t square divided by 2. So in order to prove my claim, what we need to show is that this holds. Remark that I'm not assuming anything about these random variables, about the distribution of these random variables. So phi here is the characteristic function of any random variable which has 0 first moment and finite second moment. Now at this point, I will use the expansion of phi which I presented at the beginning of this lecture. So since we have a finite second moment, remember that phi y1 of t could be written as a sum from j equal to 0 up to 2 of I t j, j factorial exponential of y1 j plus a remainder, and the remainder could be written as t2 divided by 2 r T. And RT, let me write the properties of RT here. RT, it's bounded by 4 times the expectation of y1 square, and the limit as t goes to 0 of RT, then this is 0. So I will use this formula in order to prove that this convergence holds. Now mind that here I'm not interested in the value of the characteristic function at t, but at t square root of n. So by this formula, y1 at t square root of n, then this is equal. So let's say we have the first term, j equal to 0. For j equal to 0, this is 1. Now at j equal to 1, well, the expectation of y1 is 0, so this term vanish. And then we have j equal to 2. J equal to 2, I get a minus coming from the I square, t square divided by 2. So minus t2, and this is by square root of n. So t2, 2 times n. The expectation of y1 square, the expectation of y1 square, remember I didn't write it, but this is what we are calling sigma square. So there is a sigma square here. And then plus, again I'm computing it at t square root of n, so this is plus t square 2n or t square root of n. So this is what the proposition, the expansion of the characteristic function tells me. Now I need to take the log of this expression times n. So n times the log of phi y1 t square root of n, it's equal to n times the log of this expression. So this expression, I will write it as 1 plus epsilon n. And epsilon n is what's written here. So what we know about log, remember RT, it's a complex number. So here we are dealing with a logarithm of a complex number. But anyway, what I claim is that log of 1 plus epsilon, it's equal to epsilon plus order of epsilon square. And by using this expansion of the logarithm around 1, what I get here is that this is n, then epsilon n is this term, so I have minus t square sigma square times 2n plus t square divided by 2n times r t divided by square root of n, and now plus an expression which is bounded by constant times epsilon square. So we get, well, this expression here, it's bounded by 1 over n. So let me put here constant, which depends on r, but which is divided by n square. So this r, it's just, well, depends on t, and it's bounded. Now, since we are multiplying that by n, these terms cancel, and this is what we get for the n times the logarithm of the characteristic function. And now by using this property that r converges to 0 when t converges to 0, you fix any real number t, you let n to go to plus infinity, so this term converges to 0, this term converges to 0, and what you get is that indeed the limit of this n log phi converges to minus sigma square t square divided by 2, and therefore, since this is the characteristic function of a Gaussian which has mean 0 and variance sigma square, indeed you proved that by the Lévy continuity theorem that y1 plus yn divided by square root of n converge to a Gaussian with in distribution to a Gaussian random variable which has mean 0 and variance sigma square. So this is what's called the central limit theorem. We proved it under these assumptions, and we will investigate this result further in order to try to weaken these assumptions.